this session, we shall go through some main concepts from Algebra of Matrices. Very first list of properties from this heading is for any three matrices A, B and C of the same type. Of course, they must be of the same type, then only their sum can be defined. A plus B plus C is equal to A plus B plus C. This property we call associativity of addition. What is that? Associativity of addition. For any three such matrices, it is a evident result to observe that A plus B plus C is equal to A plus B plus C. And moreover, for any matrix A plus 0 is equal to 0 plus A is equal to A, where 0 is the null matrix of the same type as that of A. If A is an m by n matrix, then this O or 0 is also the null matrix of the order of the type m by n. A plus 0 is equal to 0 plus A is equal to A, and with this property, the null matrix A, the null matrix or the 0 matrix 0 is the additive identity. In the set of matrices, of the same type, and this is the character by virtue of which we say that 0 is the additive identity. My dear friend, just like this in our real number system also, the number 0 works as the additive identity, because for any real number small a plus 0 is equal to A is equal to 0 plus A. You can recollect. Well done. Exactly and absolutely in that similar fashion, for any matrix A plus 0 is equal to 0 plus A is equal to A. And moreover, we know what is meant by 2A, what is meant by 3A, like that. What is meant by minus A also we can say. What is minus A? If capital A is a matrix, then minus 1 into A is nothing but minus A, isn't it? Okay. For any square matrix A plus minus A is equal to 0. 0 in the sense the null matrix of the type which is same as that of A, minus A plus A. And by virtue of this character or this property, we say that minus A is the additive inverse of capital A in the set of matrices. Good. Besides this, we have one more character, that is A plus B is equal to B plus A for any two matrices A and B of the same type. This also holds good, and this property is of course called the commutative property. Commutativity with respect to addition of matrices. And all these properties help us to say that the set of all m by n matrices forms an abelian group with respect to addition of matrices, of course, and this is of course a standard result in group theory. Anywhere it is from the terminology of group theory only, we could have said that 0 is the additive identity in matrices and minus A is the additive inverse of A in matrices. One more beautiful character here is A plus B is equal to B plus A for any two matrices A and B, and this we call the commutative property. Well done. We could have seen the properties regarding addition of matrices. Let us now turn our head towards multiplication of matrices. In view of multiplication, if A is a matrix of the type m by n, B is a matrix of n by p, then the product AB is the matrix CIK m by p, where CIK is equal to sigma Aij Bjk j running from 1 to n. That is the theoretical explanation, rather definition of a product of matrices, and you all know pretty well from your earlier classes that the multiplication of matrices is possible and only when if A is of the type m by n and B is of the type n by p. So the second letter here, the first letter here must match, must coincide. Then only the multiplication is possible, and in such a case only we say that A and B are conformable for multiplication. Conformable for multiplication. Okay, then in such a case, what will be the product m by p? You see here, m by p. Well, I gave you two matrices. You tell me whether the product of those matrices is possible or not. Can you have the product of these two matrices? This is 2 by 3, whereas this is 2 by 2. Can you multiply? Justly not. This is 2. These two are not matched. Isn't it? They do not coincide. Therefore, these two matrices are not conformable for multiplication. Let us now observe some more properties regarding multiplication. Suppose A, B and C are three matrices such that both AB and BC are conformable for multiplication. Then, very first property, A into BC is equal to AB into C. This property we say associativity of multiplication. Associativity of multiplication. Associativity of multiplication. Well, suppose A is a matrix of the type m by n. A is a matrix of the type m by n, and I is a matrix of the type n by n. Then what is A into I? This is nothing but A and n. Isn't it? Suppose A is a square matrix, then what happens? Suppose A is a square matrix, then n by n, n by n. A into I is equal to A is equal to I into A. I into A. Yes, of course. And by virtue of this character, we say I as the multiplicative identity. As it works as the identity, that is why only we call that matrix the identity matrix, isn't it? I is the multiplicative identity. Multiplicative identity. Previously, we could have had additive inverse. Just like that, why can't we multiplicative inverse? That is a separate heading. There is a separate history for the invertibility of a matrix capital A, and we shall go to that in due course of time, very soon, of course. Right? This is I is the multiplicative identity, and in general, AB is not equal to BA. In general, AB is not equal to BA. That is non-commutativity. What do you say about this? Non-commutativity. Non-commutativity. In matrices, in general, if A and B are any two matrices which are conformable for multiplication, AB need not be equal to BA. That also every one of us know pretty well. Every one of us know it pretty well. We all know it. Yes, of course. AB is not equal to BA. Suppose AB is equal to BA, then what happens? AB is equal to BA implies What do you say? A and B commute. Those two are commuting. That's all. A is B is equal to B. Well, there is a special case. AB is not equal to BA, but AB is equal to minus BA. Then these two satisfy anti-commutative law. What do you say? Anti-commutative law. So that is a special case of interest which is not generally asked in competitive examinations. You need not go through that at all. If A and B commute, what can you understand? What can you understand? AB is equal to BA, then we say that A and B commute. One more property, A, B plus C is equal to AB plus AC, provided both AB and B plus C are defined. B plus C is defined. What does it mean? B and C are of the same type. AB is defined. What does it mean? A and B are conformable for multiplication. What is meant by that? If A is an M by N matrix, then B must be N by P. Similarly, C must also be N by P, so that A, B and AC can be defined also. Okay, A into B plus C is equal to AB plus AC. This we call distributivity. What is this property called? Distributivity. Just like this, we have A plus B into C is equal to AC plus BC. This is also called distributive character. This is also called distributive character. Well, there are so many important and special properties regarding multiplication. We shall now go through those properties. In real number system, we pretty well know that if A and B are two real numbers such that AB is equal to 0, then one of them should happen to be 0. A is equal to 0 or B is equal to 0 or both. That is correct in real number system. But of course, in the case of matrices, if A and B are two matrices such that AB is defined, that is A and B are conformable for multiplication, that is A number of columns in A is equal to number of rows in B. AB is equal to 0 implies, need not imply that one of A comma B is 0. What I mean to say is, this AB is equal to 0 does not imply A is equal to 0 or B is equal to 0. In fact, you have A is a non-zero matrix, B is a non-zero matrix, even then you can have the product AB as in 0 matrix. Sure, you can easily have. Do you want to have the example? Observe this: 1, 0, 0, 0. 0, 0, 0, 1. It is not a 0 matrix, that is also not 0 matrix. Observe the product: 0 plus 0, 0. 0 plus 0, 0. 0 plus 0, 0. 0 plus 0, 0. Observe this. This is a non-zero matrix, that is a non-zero matrix, and the product is 0 matrix. With this character, we say that the set of matrices is not without zero divisors. There are no zero divisors in the set of matrices, isn't it? Let us make another comparison from the set of real numbers and the set of matrices. Look here. Suppose A, B, C are three real numbers such that AB is equal to AC. What can you have? And given that A is not equal to 0, what do you say? And A is not equal to 0 implies B is equal to C. We are sure to have B is equal to C. You can cancel A. Why? Because it is given that A is not equal to 0. Okay, in the set of real numbers, such things happen. You see, in matrices, AB is equal to AC need not imply B is equal to C. need not imply B is equal to C, irrespective of the nature of A, whether it is a zero matrix or a non-zero matrix. B is equal to AC does not imply, need not imply that B is equal to C. Of course, later on some cases may happen in which this implication might be correct. This will be correct when and only when A is non-singular. What is singularity and what is non-singularity we did not come across so far. We shall learn in due course of time, within few minutes of course. But for the present, A is equal to AC need not imply B is equal to C. Well, Maria, look at the board. A beautiful matrix is written there. Don't ask me why, you just do what I ask you. Find A transpose. Cos theta minus sin theta. Sin theta, cos theta. And now you find what is A into A transpose. Cos theta into cos theta, cos square theta, minus sin theta into minus sin theta, plus sin square theta. First row, first column is over. First row, second column. Cos theta into sin theta, cos theta, sin theta, minus sin theta, cos theta. Second row, first column. Sin theta, cos theta, minus cos theta, sin theta. Second row, second column. Sin square theta plus cos square theta. This is equal to 1, 0, 0, 1 is just nothing but I. Well, my dear, what do you understand by this? What do you notice from this example? A is a special matrix for which A into A transpose is equal to I. And moreover, it is not difficult to observe the same step can also be written in this form: A transpose into A. A into A transpose is equal to I is equal to A transpose into A. That quality characterizes a new matrix called orthogonal matrix. What is that? Orthogonal matrix. Actually, this must be the heading. I thought that you can understand well if I can show one example. By means of this example, I could have established this definition. So it is possible to observe such matrices A such that A into A transpose is equal to I is equal to A transpose into A. And this can happen in the case of a square matrix only. Such square matrices, such whose product with their corresponding transpose gives rise to the identity matrix of the same order, are called orthogonal matrices. In short tips to say, in brief, if A is a square matrix, then A is called orthogonal if A into A transpose is equal to I is equal to A transpose into A. This is about orthogonal matrix. This is what we say, what we can understand about orthogonal matrix. What do you mean by an orthogonal matrix? A into A transpose is equal to I. Well, Maria, look at the board. Now I am interested to introduce you one more new word, namely idempotent matrix. What is meant by idempotent matrix? This also I would like to explain you by means of an example. You see, I have given a matrix, square matrix A on the board. You please calculate what is A square. What is A square? A into A. What is A into A? 2 minus 2 minus 4 minus 1 3 4 1 minus 2 minus 3 and again A 2 minus 2 minus 4 minus 1 3 4 1 minus 2 minus 3. Come on. 4 plus 2 6 minus 4 2 minus 4 minus 6 plus 8 minus 2 minus 8 minus 8 minus 16 plus 12 minus 4 minus 2 minus 3 minus 5 plus 4 minus 1 plus 2 plus 9 11 minus 8 3 plus 4 12 16 minus 12 4 2 plus 2 4 minus 3 1 minus 2 minus 6 minus 8 plus 6 minus 2 minus 4 minus 8 minus 12 plus 9 minus 3. What special result you are able to see? You are able to get A, isn't it? So the beauty of this example is A square is equal to A. A square is equal to A. My dear friends, if at all such thing happens in the set of real numbers, what happens? If A square is equal to A, two cases will arise. Either A is 0 or A is 1. Here, capital A is neither a null matrix nor a unit matrix, isn't it? Even then we are able to have A square is equal to A. Those square matrices for which A square is equal to A square is equal to A are called idempotent matrices. What are they? Idempotent matrices. This is the special name that can be given to such matrices A for which A square is equal to A. I think you could have understood. You may ask me, why is it necessary to give the example at the beginning? So that you can believe that there are such matrices. Yes, we can have such matrices. A square is equal to A. And such matrices are of course called idempotent matrices. What is the special name? Idempotent matrices. What is the character of idempotent matrix? A square is equal to A. Previously we could have had one more name. What is that? Orthogonal matrix. What is meant by orthogonal matrix? A into A transpose is equal to I. Well, at this juncture I have forgotten to introduce you one more word, unitary matrix. What is meant by unitary matrix? We shall see. If A into A transpose is equal to I is equal to A transpose into A, what is A called? What is A? Orthogonal matrix. Similarly, if A into A power theta is equal to I is equal to A power theta into A, then we call A as a unitary matrix. What is that? Unitary matrix. Okay, I think you are getting confused. We shall speak of this later. You just think of the idempotent matrix only for the present, because the example for the idempotent matrix is readily available on the board. This is A. We have seen, we have calculated that A square is equal to A. Such matrix which equals to its square, that is A square is equal to A, is called an idempotent matrix. What is this called? Idempotent matrix. Previously, we have known that A into A transpose is equal to I is equal to A transpose into A implies what is A? A is called an orthogonal matrix. What is that? Orthogonal matrix. In a similar fashion, if A into A power theta is equal to I is equal to A power theta into A, in this case A is called a unitary matrix. What is that? Unitary matrix. You see, I'm not focusing my attention much on this unitary matrix because they are rarely in use and we come across such matrices so rarely. That is why it is just enough to know its name. What do you mean by a unitary matrix? If A into A power theta is equal to I, then we call such square matrix capital A is a unitary matrix. I think you know what is meant by A power theta. In this session itself, we could have recollected it. What is A power theta? Transpose of the conjugate or conjugate of the transpose, together called transposed conjugate of A. And in short tips to say, we represented it by the symbol A power theta. That's all. So at a time we have seen two names, orthogonal matrix and unitary matrix. This is purely when the matrix elements of the matrix are real numbers, and this can be applied even when the elements of the matrix are complex numbers. One more thing you say, if every entry of a square matrix of an orthogonal matrix is a real number, then it is unitary also. Surely, isn't it? Okay. Next name and next example we shall be looking at. There are some matrices, some square matrices, whose square is equivalent to the unit matrix. If A square is equal to I, then it is called involutory matrix. What is that? Involutory. A is called involutory. Involutory. And the ready-made example of an involutory matrix is I. You know I square is equal to I, isn't it? Yes, it is involutory. And there are so many examples there, and it is time taking and useless. Of course, you mind in your mind A square is equal to A square is equal to I implies A is called involutory matrix. What is that? Involutory matrix. Nilpotent matrix. Nilpotent matrix. A beautiful and useful concept among matrices is nilpotency of matrices. What do you mean by a nilpotent matrix? There are some square matrices such that, suppose A is a square matrix, you find A square and then find A cube and then find A power 4. You may be getting 0 at A power 4. If A power 4 is 0, A power 5 is 0, A power 6 is 0, A power 7 is 0, A power n is 0. A power n is 0. So if there is a positive integer n such that A power n is equal to 0, then A is said to be nilpotent. Among all these, A square is not 0, A cube is not 0, A power 4 is 0. This implies A power 5 is 0, A power 6 is 0, A power 7 is 0, and so on. Out of all these exponents, what is the least exponent? 4. In such a case, we say that that square matrix is nilpotent with the index of nilpotency as 4. With the index of nilpotency as 4. Okay, do not get confused. I like to give you the clear picture of the two words. If there exists n belongs to n such that A power n is equal to 0, then A is called a nilpotent matrix. That is the true definition. Also, the least positive integer m such that A power m is equal to 0 is called index of nilpotency. What is that? Index of nilpotency of A. You can ask me a doubt. Why is it necessary to define the index of nilpotency? Suppose you have at a particular step or in a particular question that a power 6 is equal to 0. What do you say about a power 5? What do you say to a power 4? What do you say about a square? It's not given. Of course, if a power 6 is 0, a power 7 is 0, a power 8 is 0, and so on. So to have a clarity about the exponent to which a is right, then we will be getting 0. The index of nilpotency has been introduced. If a square is not 0, a cube is not 0, a power 4 is not 0, and a power 5 0, so 5 is the very first natural number or the least natural number for which a power 5 is 0. That 5 is called index of nilpotency, or a is said to be nilpotent with index 5. Suppose we have a square is equal to 0, just, and a not equal to 0. What can you say about this situation? A is not equal to 0 and a square is equal to 0. What can you say about this situation? A is nilpotent with index 2. With index 2. If 2 is the index, nobody asks about a power 5. Why? Because if a square is 0, a power 5 is 0 cube. Again 0. So nobody asks that doubt. So it's very important to know the index of nilpotency. It is very important to note the index of nilpotency. And it is quite interesting to have an example of a nilpotent matrix, and we shall be having that. Well friends, consider the matrix given on the board. We are to test about the nilpotency of this matrix. First of all, what is a square? A into a, 1, 1, 3. 5, 2, 6, minus 2, minus 1, minus 3, into again 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3. What is a square? First row, first column. 1 plus 5, 6, minus 6, 0. 1 plus 2, 3, minus 3, 0. 3 plus 6, minus 9, 0. 5 plus 10, 15, minus 12, 3. 5 plus 4, 9, minus 6, 3. 15 plus 12, 27, minus 8, 9. 18, 9. Minus 2, minus 5, minus 7, plus 6, minus 1. Minus 2, minus 4, plus 3, minus 1. Minus 6, minus 12, plus 9. Minus 2, minus 6, minus 12, plus 9, minus 3. This is about a square. We have got zeros in the first row, but these are not zeros. A square is not 0. Now let us try to find a cube. What is a cube? A square into a. What is a square? 0, 0, 0, 3 minus 1. 0, 3 minus 1. 0, 9 minus 3. What is a? 1, 5 minus 2. 1, 2 minus 1. 3, 6 minus 3. Come on, find the product. Surely first try is 0. 0 into 0 into 0 into z, etc. It is 0, 0, 0. Undoubtedly. Come on, think of the second row. 3 plus 15, 18, minus 18, 0. Again you observe the remaining elements. Surely you will be getting 0 at all. No problem. What is your observation? A square is not 0. A is not 0, a square is not 0, a cube is 0. What can you understand? A is nilpotent with index 3. Well, is there anybody who asks about what is a power 5? It is 0. Why? Because a cube is already 0, a power 4 is 0, a power 5 is 0, a power 10 is 0, a power n is 0 for any n greater than or equal to 3. Well, this is nilpotency, and the index of nilpotency, and this is the beautiful example of a matrix which is nilpotent, and the index of nilpotency for this matrix is 3. There might be square matrices which are nilpotent with the index 2 also, we do not know. There might be. This is what we say about nilpotency. The next word before us is periodic matrix. We could have had periodic functions and period of a function, but what is the periodicity of a matrix, square matrix? It's new, of course. There are certain matrices. Suppose there is a matrix, square matrix A, such that A power k plus 1 is equal to A. If at all such things happen, that there is a positive integer k such that A power k plus 1 is equal to A, then A is said to be a periodic matrix. And the least such k is said to be the period of the matrix. Previously, we could have had a matrix with the quality A square is equal to A. Could you remember it? Yes, you're right. It is an idempotent matrix, you know. So, idempotent matrix is also periodic with period 1. Why? Because A power 1 plus 1 is A. So, it is said to be periodic with period 1. Well, let us have a full sentence for this matrix, because this is a new matrix. Very few textbooks include this particular concept. What is a periodic matrix? Look here. If there exists k belongs to n such that A power k plus 1 is equal to A, then A is periodic. The least value of such k belongs to n is called the period of A. This is about periodic matrices. Well, my dear, not only this, there are so many other matrices. New names must also be introduced in our journey of matrices, as and when they are required, as and when they are meant, as and when it is possible to describe them, we go through them. Okay, right. For the present, let us put a comma, not a full stop, for these types of matrices. There are so many other things there before us to look at. We shall be touching them also.